Do you know the world's most common psychoactive drug of choice? Is it cocaine, methamphetamine, or perhaps even nicotine? Multiple studies, including one 2019 study done by Shireen M. Azab, researcher at Cairo University, discusses caffeine as the world's most extensively used legal psychoactive medication, highlighting its safe categorization by the FDA. As the world's most prevalent psychoactive substance, caffeine weaves itself into the fabric of our society. But how much do we really understand about this ubiquitous molecule? From its intricate molecular structure to its profound impact on human mood and physiology, caffeine is more than just a wake-up call. It's a pharmacological phenomenon that holds many pearls worth exploring. With these pearls, we will hold a better understanding of mechanisms that reappear in a myriad of other drugs. Caffeine, scientifically known as a trimethylxanthine, stands out as a pivotal stimulant in numerous beverages. Its structure, characterized by the addition of three methyl groups, hence the prefix tri, to a xanthine base, plays a crucial role in its biological activity. The basic chemistry reveals that these methyl groups at positions 1, 3, and 7 significantly enhance its ability to influence human physiology. Comparatively, caffeine shares a striking resemblance with adenine, a nucleotide found in your deoxyribonucleic acid, which normal people call DNA for short. This similarity to adenine in the purine scaffold both molecules share underpins caffeine's ability to interact effectively with adenosine receptors in the human body. Understanding this structural relationship is key to deciphering how caffeine manipulates brain chemistry and bodily functions on a molecular level. As is the law, structure always dictates function. Adenosine receptors, adenosine receptors, specifically those found in the brain, play a significant role in governing sleep, relaxation, and many other physiological processes. Caffeine's ability to bind to these receptors, particularly the A1 and A2A, inhibits their normal function, which is to promote relaxation and sleepiness. This interaction is a classic example of competitive inhibition. By occupying the adenosine-binding sites on these receptors, caffeine effectively blocks the hyperpolarizing because adenosine cannot bind while caffeine is in the way, leading to increased alertness and wakefulness. Visualizing this molecular dance helps clarify why caffeine is such a powerful stimulant. Upon ingestion, caffeine quickly travels to the brain, where it starts its primary action of blocking adenosine receptors. This blockade results in a cascade of sympathomimetic effects across the body. Adrenaline is released, heart rate increases, and alertness sharpens. This immediate impact on cognitive functions is what makes caffeine a popular choice for those needing to stave off sleep or enhance concentration. But it's not without repercussion. While the stimulatory effects of caffeine can be beneficial, it is important to remember that adenosine is still building up in the body. Therein, the energy one may feel is not energy at all, but rather an illusion. The brain simply thinks it's not tired. Excessive intake leads to the body adapting to the continuous blockade of the adenosine receptors. It does this by simply growing more receptors through a process called recruitment. After which, more caffeine is required to block the increased number of receptors. This is called tolerance and can be observed in other drugs as well. Further effects of excessive caffeine use, greater than 400 mg per day, include insomnia, digestive issues, increased heart rate, and even more severe conditions like anxiety disorders. Long-term high consumption can exacerbate these issues, leading to chronic health problems and dependency. Understanding these mechanisms is crucial for deep understanding on mechanisms that are present in other drugs. As discussed earlier, when caffeine is consumed, it acts as an adenosine receptor antagonist, meaning it blocks the binding of adenosine to its receptors in the brain. However, when the caffeine wears off, the adenosine that has been building up in the brain suddenly binds to all their receptors. This binding causes a cascade of events, including the activation of potassium channels and the inhibition of calcium channels. As a result, there is a sudden hyperpolarization of nerve cells, which means the electrical potential across the cell membrane becomes more negative than the resting state. This sudden hyperpolarization can lead to various effects, which may include sudden lethargy, headaches, chills, decreased concentration, and mood changes. The hyperpolarization of nerve cells can disrupt normal brain activity and contribute to feelings of fatigue and discomfort. We commonly refer to this as the crash. In this video, we covered not only caffeine's mechanism of action and molecular structure, but also briefly mentioned terms such as competitive inhibition, hyperpolarization, and tolerance. Stay tuned for further content where we will see the recurrence of these terms and much more when we discuss the why behind the need for this knowledge. If it pleases you, please like and subscribe for more content. Sorry, union rules for all YouTube creators. Thank you for watching the first video ever posted on EMS Provider Hub.